Dear students, welcome to Digital System Design using Verilog class. We are in module 3. In the last class, we have discussed few topics on IC packaging as well as PCB, IC packaging and printed circuit boards. In today's class, we will be discussing in brief about interconnection of various signals and signal integrity. Right, so what is signal integrity is nothing but it is minimizing the effects caused by the distortion and noise on the signal while propagating through the bond wires, packaging pins and PCB traces. That is what signal integrity is all about. We need to safeguard the actual signal from various effects that is caused by distortion as well as the noise. Okay, so propagation delay in PCB trace is around 150 millimeter per nanosecond, and in case if two PCB traces, that means two connections on the PCB are having a different length, then there will the skew rate, that is expected clock value to the actual clock value. If there is a difference at the arrival point, if it is significant, then we need to take care in the PCB design itself. So that is what signal integrity is, safeguarding the actual signal from distortion and noise that has caused while the signal starts propagating through the bond wires, packaging pins and PCB traces. There is an effect called ground debounce. Let us understand what is ground debounce. It is nothing but, as you can see, IC packaging, IC within a package is what you are seeing. These are the connections that has happened to various components of the IC in the package. So transient current flows when an output switches logic level. So at the output side, when the switches start changing the values, that is logic level 0 to 1 and 1 to 0, parasitic inductance will cause, and it is going to change the voltage on the power supply side as well as at the ground signal side. So it also impacts the drivers through the spikes that has got generated. So ground debounce is one of the parameter that has to be taken care. Due to the switching, ground debounce happens. So how do we minimize the debounce? Is nothing but we need to use bypass capacitors closer to the PCB trace. So bypass capacitors has to be used between ground and positive plus volts, okay, supply towards the ground of around 0.01 microfarad to 0.1 microfarad close to the packaging pins we need to use. Also, we can minimize the debounce by using separate planes for transmitting the ground as well as plus volts. That you can notice from this figure, that signal layer followed by power plane, signal layer, again ground plane, bottom again signal layer. So separating these lanes for transmitting the ground as well as supply will also minimize the effect of ground debounce. Okay, so that is one more thing. And transmission line effect. Okay, so what is the transmission line effect? Let us understand this. So basically it occurs when rise time is compared to path delay. Signal rise time, if it is comparable, that means if it is significant enough compared to the path delay, then it will lead to a transition. Okay, also a factor called overshoot, as well as it also leads to ringing, okay, fluctuation in the signal, right? So ultimately this overshooting and ringing will lead to false as well as multiple switching, unwanted activity that takes place. So how do we minimize this? Is we need to use a PCB layout techniques. We have to use a proper PCB layout techniques in order to minimize these effects. As you can notice, voltage output high level, input high, input low, output low, there will be a ringing effect, undershooting and overshooting problem will be there, which will lead to false or multiple switching. Okay, so and there is another effect that is called EMI, electromagnetic interference. Due to the switching of various devices, due to the transition or switching of various devices on the PCB, Energy radiates from PCB traces as well as it induces noise in other systems. Okay, switching in one of the devices may have a electromagnetic interference on the nearby devices. It will also lead to a crosstalk. Nothing but radiation to other traces in the system might also happen, especially the adjacent parallel traces. That we can minimize this EMI. How do we minimize this EMI? Because there will be a switching, there will be a transition that takes place in the circuits, values, voltage levels. So how do we minimize that? Is we have to properly plan the PCB layout. Sleeve rate limiting can also minimize all these factors. Next is about differential signaling. What is differential signaling? Is we have to transmit the signal, and at the receiver side we need to be able to recover the original signal by nullifying the effect of noise. That is what differential signaling is. So the technique used here in differential signaling is we have to transmit the original signal S along with its negation. Okay, transmit a signal SP with its negation called SN, right? Both SP and SN will get added with the noise in the channel. While transmitting, both will get added with the noise. When we subtract these two, SP minus SN, noise will get cancelled out, and the remaining term is SP and its negation SN. This is one way where we can recover the original signal without the effect of much added noise in the signal, right? So this is about differential signaling. Difference is nothing but original signal and its negation. We have to take a difference of that. We have to transmit both. You can see that in the diagram, SP and SN both are getting transmitted. In the channel there is a possibility of addition of noise. That is what it is represented. SP plus V noise is addition of noise to the original signal, addition of noise to the negated signal. When we take a difference, both the noise will get cancelled out, and the remaining term is SP minus SN, that is original signal and its negation, right? So this is about differential signaling. Till now in these videos I have tried to give you a brief introduction to the topics that is there in the third module, that is implementation fabrics. In the class we will be discussing much more in detail about all the topics which we have seen in this third module.